going. Okay. So, all right. Okay. So, what we're going to do today is extend our story beyond free particles. So remember, we've basically been working to get insight into how to work with freely propagating scalar particles, which are important for the Higgs mechanism, spinors, which are important for all matter, everything that you're made of is spinor, and then vector particles, which we'll find play a very important role in interactions. So we'll discover the role they play today. So we have the free Lagrangians. And what I mean by free, of course, is just these particles or these field fluctuations, they just move kind of at a constant velocity because there's no force acting on them, okay? So we have the scalar story, which is 1/2 d mu phi plus 1/2 mc over h bar squared phi squared. And I'm writing down the Lagrangians rather than the equations of motion, which for reasons which will become obvious in due time. H bar c, psi bar, gamma mu, d mu, psi, plus, and for those of you who are visiting the class, much of what we're doing, the reason the notation looks different than what you've seen before is everything here is purely relativistic. So there's none of this which is not relativistic, so everything's four-dimensional, et cetera, et cetera. So if I say it's a vector, it's a four-component vector versus a three-component vector. A mu, where F mu nu is defined as d mu, a mu minus d mu, a mu. Okay, so those are the Lagrangians, which are basically the kinetic term of an ordinary three-dimensional Lagrangian. So it's like 1/2 mv squared for the kinetic term in a Lagrangian. These are the relativistic generalizations of that for fields. That's all they are. But just as this describes a free particle because I don't have any interaction, this thing is just going to reduce to mass times acceleration equals 0. Okay, these will similarly do that. Of course, the reason these are different is because this is a scalar particle. This is a spinor, so you can transform the spin, and then this is a vector, it has spin, and you can transform the spin of that. So that's why these equations look different, although they all contain the first equation. Okay. Now remember, if you notice, every single part of these equations is at most quadratic. And it's a quadratic either in the field phi, in the first case, or in the derivative of the field. Okay, so this term is obviously quadratic in derivatives of the field, and this term is obviously quadratic in the field. This is quadratic in the field and the derivative of the field. That's a weird combination, but that's spinors. And this is quadratic in the spinors, and then this is quadratic. This is linear in the derivative, but so is this, and these are multiplied together, so it's quadratic in the derivatives, and this is quadratic in the fields, okay? That is going to be an important observation, which we'll look at later in more detail. So the question is, what do interactions look like? Okay? So again, I have fields multiplied by fields in this story. It's all the field multiplied by itself, or its derivative. What would interactions look like? Henry Trolson. Henry, are you here? Yes. What do you think interactions might look like? Another difference? Well, no, actually, I'm thinking of adding on so in the standard three-dimensional case, if I have interactions, I add in a potential term. And this potential term is usually set up to be a background gravitational field created by the Earth and then a particle's gravitational potential in that. That's the way this story kind of plays out. You can do that this way. It's fine. It doesn't really matter. But so I'm going to add terms to these Lagrangians that represent interactions. And my question is, what kind of interaction terms do you think I would add in?
Yes, I mean some sort of multiplied interaction between pairs.
Yeah, so if I added into this equation phi times a mu, where the phi comes from this equation and a mu comes from this equation, then this is an interaction of a scalar and a vector. So they're basically just the fields multiplied together. You could multiply this by the derivative of this. Okay, that's fine too. But the point is, if you're multiplying factors with different fields in them, then you're dealing with an interaction. Does that make sense? Or if you go above quadratic, if you do cubic or quartic or whatever, like if I do phi cubed, this would be an interaction, a self-interaction of the phi field with itself. Okay? So the kinetic terms only involve quadratics if I go above quadratic, or if I multiply different fields, I'm dealing with interactions. Okay? So if you think about it, there's kind of a gazillion different interactions you could introduce to these, right? Right? So what is dictating what form of interactions we should have? Well, this is the point of this story, symmetry. Okay? So, the symmetry that is going to dictate how these things should be changed is what we call local gauge symmetry. And I'll go through exactly what I mean by this in a moment. But the local gauge symmetry dictates the final interaction terms. Okay? Now, this is a program, and I'm going to lay down the steps to the program for you, and I'll do that. Actually, I'm going to erase this comment and put these steps here so that I've got that part of the board to play with. Okay? So I'm basically going to give you the formula for imposing local gauge symmetry. First of all, begin with a free matter Lagrangian. Okay? Joey, which of these three Lagrangians do you think would be relevant for free matter?
1/2.
Yeah, because all matter, everything that we're made of, is spinor. So we got to use the spinor part, spinor term. So that's also called the Dirac Lagrangian. And we want this to have some global symmetry. And I'll review what I mean by global symmetry in due time. I just want to write the steps up here, and then I'm going to go through the steps in an example. So next, what we want to do is we want to promote the global symmetry to a local gauge symmetry. And I'll explain exactly what I mean by that in due time. With the addition of compensating gauge field. Okay, it turns out that if I start out with this Lagrangian and I recognize a global symmetry, to make it a local symmetry will actually require me to add a new field to the story. Okay? But this gauge field must transform under the symmetry in question in a specific way. This will induce interactions. So we'll find that by promoting, by promoting a global symmetry to a local one in the proper way, we will automatically get interactions in the theory. This is my statement that the interactions in the standard model and in general relativity, in fact, all four fundamental forces all come from demanding symmetries. And it's demanding that they be local. Okay? And again, I'll describe what that means in a bit. Step 3, well, it turns out that the gauge field that you've added is just a background. It cannot propagate, it's not got a kinetic term. So we allow the gauge field to propagate by adding a field strength. To L. Okay? And then there's a fourth step. Anybody know what the fourth step is? Okay? Anybody want to skip straight to the fourth step? Okay. So again, these are a bunch of words. There's a bunch of underlying math, which we'll go through, okay? But this is the story, and there's no better way to sort of explain what's going on than to look at an example, okay? Turns out, normally you start with a cartoon example, but I'm gonna go straight for the throat. I'm going to give you an example which you should all be very familiar with, although I highly doubt it, okay? So at the end of this example, you'll go, oh, okay? So here we go. We're going to start with just this second Lagrangian. So h bar c, psi bar, gamma mu psi, gamma mu, d mu psi, plus mc squared psi bar psi, where you should remember that psi bar is I psi dagger gamma 0. Okay, where gamma is the zeroth, or gamma 0 is the zeroth of the gamma matrices. Okay? And then, of course, remember that psi is a 4-component spinner. For those of you who are just visiting, it turns out that spinners in 3 dimensions have 2 components, and vectors have 3 components. But in 4 dimensions, vectors have 4 components, and spinners have 4 components. So these are 4-component spinners. I shouldn't call them spinner vectors, they're just spinners. Okay? Now, those spinners are complex. They have 4 elements, and each element can be a complex number. The fact that they're complex means that this could be a symmetry. If I take psi and I basically send it to psi prime, which can be gotten by multiplying by a complex exponential, okay, where q is some constant, and so is phi. Okay? Now, the fact that I have 2 constants there might seem a little stupid because the product of 2 constants is a constant. Why are you doing 2 constants? Da, 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 da. In a minute, we'll change the story. So having 2 terms there is going to play a very important role. But for now, it's going to look a little silly. Okay? Now, if psi transforms like this, then we can immediately conclude that psi bar transforms as psi bar e to the minus I q phi. Okay? If that's not obvious, just take my word for it. Everyone in the class should realize why it should be obvious. Okay. And the minus here that's popping up is just due to the fact that you have to Hermitian conjugate it, and that includes complex conjugation, so that's why you get a minus in front of that I. The rest of the stuff is just getting the vectors aligned and everything. Okay, so now what I want to show you is that this transformation and this corresponding transformation for psi bar, these are a global symmetry of the Lagrangian. Let me show you. Let me just erase these to get some room. So if I ask how the Lagrangian changes, it becomes the following. H bar C psi bar e to the minus iq phi. This is just transforming the psi bar term. Gamma mu d mu e to the iq phi psi. Okay, I mean, I could have written this as h bar c psi bar prime gamma mu d mu psi prime, but I'm just going ahead and plugging in what psi bar prime looks like and what psi prime looks like. Okay, just doing a little shorthand. All right. Plus, of course, mc squared psi bar e to the minus iq phi e to the iq phi psi. Okay? Now, Connor, you can do one of the two terms, but tell me what happens to one of these two terms under that transformation. It doesn't matter, you can pick which one.
One of them?
One of them.
Okay, well.
You want to do the first or the second term?
Oh, the second one.
Okay, what happens?
That's one.
Yeah, this is just e to the minus iq. Look, folks, this is simple math. E to the minus iq phi times e to the, and these aren't even matrices. These are just like numbers, complex numbers. That's one, okay? So this is going to give me back mc squared psi bar psi, okay? Which of course is that term right there. This term is a little more work, but if you think about it, this whole thing is a constant. Because it's a constant, you can move it past the derivative. In fact, it's just a number, so I can not only move it past the derivative, I can also move it past this gamma matrix. But that means I can join it up with this and it'll cancel. Okay? So at the end of the day, we just get back h bar c psi bar gamma mu d mu psi plus that term, which of course is what we started with. Okay? So this global symmetry is a symmetry of the Lagrangian. If I enact this transformation on the Lagrangian, I get back the Lagrangian. Is that clear to everybody? Simple story. Okay? Now we want to localize it. And in order to localize it, we just change one small part of this story. We let the phi no longer be constant. We let phi depend on where you are. That is, instead of phi being a constant, phi can be a function that depends on where in space-time you are. That is a local symmetry. Okay? Remember the example I gave at the beginning of the semester when I took the dots and I said if you shift them all globally, then you get the same thing. But if you do them locally, that is, each dot gets a different shift, then this is not symmetric. But if instead we're taking circles and we're just spinning each one of them, if I spin them all by the exact same angle, I get the same thing. If I spin each of them by a different angle, I still get the same picture. This is global and locally symmetric. This is globally symmetric but not locally symmetric. We're going to promote these global symmetries of this to local ones, but it's going to require deforming it a bit. So let's do it. Okay. Well, first of all, this equation or this expression is completely unchanged. I just have to put in this x mu dependence on every phi term. Okay? All right. Drew. I'll do one if you do the other. Which one are you going to do?
If I look at my notes, I could do either. The second one's a lot easier.
Yeah, the second one's a lot easier. Okay, so what happens in the case of the second one?
Still 1.
It's still 1. The fact that phi is a function doesn't matter. You still got e to the minus iq times e to the plus iq. They combine to give you 1. So this last term is still invariant. Okay? Where, I mean, for those of you who are visiting, you should bear in mind that psi depends on position. I'm just suppressing that because otherwise I've got position dependence all throughout. Psi depends on position. It's the field, and it can vary from point to point. Okay? I just don't write that because it would be a headache. Too many of x mu's. For this one, for the phi, I want to do that because we're changing that story. Okay, so I'll do this one. Let's see. Ooh. Well, I mean, can I grab this and move it past the derivative? No. I can't simply grab this term, which has position dependence, and move it past the derivative with respect to position. So let me ask, Jack K, where are you? Jack. Is this Lagrangian invariant under the local transformations?
I would say no.
No, it's not, because if I could move this exponential across the derivative, then these would cancel, and I'd get back to what I started with. But I know if I try and move this past the derivative, I'm going to get some extra terms. Okay? So this Lagrangian is not invariant under the local form of this transformation. Okay? Well, it turns out we can make it invariant. All right? So in order to make it invariant, what we're going to do is we're going to introduce a new derivative. Okay, we're going to change the derivative that we use. And this new derivative we will call capital D mu. And this new derivative will be the old derivative plus I times Q times A mu, where A mu is a field. Okay? So this is the same constant Q as in these transformations. Okay, so I'm not just picking a random new constant, it's the same Q that enters into these transformations, and we'll identify what that Q is in a minute. However, notice this new field that I've introduced to the story is not a spinor field. It's a vector field. It's got that little vector index. Okay, it's one of these A mu's. All right? Now, this is the first deformation that we're going to make. So let's see how this plays out. All right, so I'm going to basically replace this with capital D. All right. And I can go ahead and write out what this looks like. Actually, I'm going to skip this. And I'm going to rewrite the Lagrangian in terms of this capital D. So h bar c psi bar gamma mu, capital D mu psi plus mc squared psi bar psi becomes h bar c psi bar gamma mu lower d mu psi, and then I basically replace the lower d mu with the iq a mu and yet an identical term. Oops. Okay. All I've done is I've replaced the capital D mu with d mu plus iq a mu. That's all I did. And then of course we've got the mc squared psi bar psi. Okay? Now what we're going to do is we're going to let these transformations go, but we're going to have to add to the story the transformation of A mu. Now, one question I might ask is, these are how the size transform. How does the A transform? Sam. Oh yeah, I knew you were in here. Sam, how does the A transform?
I'm not sure, but why are you allowed to do the part to change the partial which have to move to the D?
Why am I allowed to do this?
Yeah.
Well, I'm just changing my Lagrangian to hopefully make it symmetric. This is just a guess. Okay? But I know how the psi and the psi bar transform. How does that A mu transform? Does anybody know? You shouldn't. We don't know how it transforms. In fact, we're going to use this to make sure the whole thing is symmetric. We're going to find what we need for this transformation by demanding that this thing be unchanged. So you should not know. We haven't figured it out yet. That's a very important part of the process. Okay, so let's do it. L goes to L prime. And let's just shove everything in. H bar C psi bar e to the minus IQ phi of x mu. Gamma mu d mu e to the IQ phi x mu psi plus IQ H bar C psi bar e to the minus IQ phi of x mu. Gamma mu A mu prime e to the IQ phi of x mu psi. And I'll just go ahead and say MC squared psi bar psi because we've already established that that last term is invariant. Okay, so I won't write all that detail in. Okay? All right, now here we go. First of all, what I'm going to do is I'm actually going to move this past the derivative, but I'm going to generate a new term because this is really just the product of two functions, and I know how to take the derivative of the product of two functions. It's just the product rule, right? Okay, so this is going to become H bar C psi bar e to the minus IQ phi of x mu. And it turns out I can just shorten what I'm going to write in the following form. Gamma mu IQ d mu phi x mu e to the IQ phi x mu psi plus e to the IQ phi x mu d mu psi plus IQ H bar C psi bar gamma mu A mu prime psi plus MC squared psi bar psi. Okay? So in this case, I'm acting on the exponential with the derivative. And in this case, I'm acting on psi with the derivative. So this is literally just the product rule for this derivative right here. The derivative of this pair of functions. Everybody on board with that? Good. Okay, so if I stare at that for a moment, any questions? Okay. Well, let me write this in a cleaner way. So I can say, all right, this is H bar C psi bar. Well, hold on. The derivative is acting on this, which means this is not being acted on by the derivative for this term right here. That means I can move this over and cancel this. Nice. Okay, so this first term is going to give me gamma mu d mu psi. Okay, so that's taking this term and combining it with this. Okay. Hold on. Yeah, no, you're right. Sorry. It's this guy that I can combine with this. I'm just doing it in the opposite order. Sorry. You're right. It's this guy with the, I was like, where does this IQ go? And what about this? Hell, I don't know what's going on. No, you're right. It's this guy that I can trivially combine with this to just give me back this term. This guy's going to generate something new. Here we go. Plus IQ h bar c psi bar gamma mu d mu phi of x mu times psi. Okay? Plus this term, plus I, Q, H bar C, psi bar, gamma mu, A, mu prime, psi, plus of course, this little hanger on here. All right? Now are you ready? Here's the magic. We have still not specified how A transforms. But notice, A is sitting in this bundle of stuff in a very, very similar way to d mu phi. They have all the same coefficients. So it turns out, if A mu prime, now notice, this term is exactly what we started with. This term is exactly what we started with, okay? This term, well, it's kind of like what we started with, but if I make A mu prime A mu minus d mu phi of x mu, then if I plug this in for A mu prime, this term is going to cancel that term, and I'm going to be left with A mu. That is, I'm going to be left with this term. Okay? So if this is the case, then L goes to L prime, which is L. That is, by introducing this A mu to the derivative redefinition, and imposing that A mu transforms like this, which is very, very different than this, way different, okay? Then it turns out that my Lagrangian is invariant under this local transformation. In fact, let me just go ahead and write down what it looks like. It looks like this. L prime equals h bar c psi bar gamma mu d mu psi plus I q h bar c psi bar gamma mu a mu psi plus mc squared psi bar psi. Okay? What do you notice? What is that?
Interaction term.
That's an interaction. This is the interaction of the spinor field with this new gauge field. It's forced on us by demanding that the symmetry be local. Okay? We started out with this free Lagrangian piece, this kinetic term, with a global symmetry. There was no interaction. But by demanding that that symmetry be local, we were forced to introduce A, and as a consequence, we get interactions between A and psi. Okay? They're forced on us. We could not do without this term. Yes?
How do we know to introduce another A instead of, like, for example, another spinor?
Because you're fixing the derivative. The derivative operator is vector-like. It's dual vector-like, actually. But so whatever you're adding to it has to be dual vector-like. Okay. Now, let's do step 3. That is, realize that if you tried to write down the equation of motion for A mu, you wouldn't really get anything because there's no derivative term of A mu in here. There's the derivative terms of the psi's, and then there's the interaction of psi with A mu. This Lagrangian basically describes how the psi field would interact with a background version of A mu. You're not solving a differential equation, an equation of motion for A mu, you're just saying A mu has this profile, that's going to cause psi to behave in this way. However, we want everything to propagate. We want everything to have a kinetic term. So what we need to do is add a kinetic term for A mu. Make sense? Okay, so let's do that. Wait a minute. What is this? This is the kinetic term for a vector field. We can just add in this bad boy. If we add this in, then both psi and A mu can propagate, and in addition, they will interact with each other. This is a beautiful story. Okay, so let's just add that term in. Okay, so if I call this, well, actually, what I'll say is that I won't write it. Allow A mu to propagate, and then L goes to L plus L1, where L is just this thing, and then I'm going to add in this term. Okay? Now here's an important observation. We know that this is invariant under these transformations. We should ask if this is invariant under those transformations, because we can't add it in if it's not. It'll screw up that part of the story. Okay? So let's ask, is L1 invariant? Well, let's do it. L1 goes to L1 prime, and again, I'm just going to write out what the F mu components are in terms of these expressions. So this is going to be 1 over 16 pi d mu A nu prime minus d mu A mu prime. And instead of doing F with two upper indices, I'm going to go ahead and translate these to lower indices. It makes more sense that way, but that means I'm going to have all these metric factors in there which raise the indices. So these are going to be eta mu lambda eta mu rho, d lambda A rho prime minus d rho A lambda prime, plus 1 over 8 pi mc over h bar 1 v squared, A nu prime, eta mu nu A mu prime. Okay? Again, the only reason I'm lowering this thing to a lower one is because I've already figured out how the lower term should transform. So now I've got nothing but lower terms, and so I can just use this transformation rule, replacing A prime everywhere it appears by this. Okay? So if I do that, I'm going to get 1 over 16 pi. Oh boy, here we go. D mu A nu minus d mu phi. Okay, that's just replacing this A nu prime with A nu minus d nu phi. And I'm going to leave off the position dependence of the phi's because there's going to be too many of them. Minus, now I'm going to replace this one. Okay, so that's this term in parentheses. Now we'll do the eta mu lambda, eta mu rho, and then we're going to have d lambda A rho minus d lambda d rho phi minus d rho A lambda plus d rho d lambda phi. And then last but not least, plus 1 over 8 pi mc over h bar squared, A nu minus d nu phi, eta mu nu, A mu minus d mu phi. Okay? Caleb, I'll take one if you take the other. Which one you want to do?
The first one.
Really? Okay, fine. Go for it, man. What do you notice? Does anything cancel?
Yeah, it looks like the first two terms cancel each other in the second. So the
These
first-
two terms?
Yeah, no.
No, this is the d nu a nu, this is d nu d nu phi. What about these
Yeah,
two
first
terms?
two, yeah.
Do those cancel? I mean, this is d nu d nu and this is d nu d mu.
Right.
Can I swap the order of partial derivatives? Yes, you can. So I can just swap this to d mu d nu, this is plus, this is minus, these cancel. First term's easier. What about this? D lambda rho and d rho lambda. Those cancel as well. Boom. Guess what you get? You get 1 over 16 pi d mu a nu minus d nu a mu eta mu lambda eta nu rho d lambda a rho minus d rho a lambda. Okay? You get exactly what we started with. That first term is invariant. Awesome. My turn. This is not invariant. I mean, look at it. If you want this to go back to, this, you're going to get that factor from these two a's, but you're also going to pick up all of these derivatives. And they're going to screw up the story. Okay? They're just going to screw it up. So, it turns out that you cannot impose local gauge symmetry in this fashion. Jet, look up. Unless, what?
Unless A is symmetric? Oh, unless it's massive.
Exactly. If the mass of A is 0, this whole term vanishes. And the story works. Okay? So, if we do this, then we can add this to the story up here, and the entire story is locally gauge invariant. Pretty sweet, huh? All right, I'm going to erase all of this and just write up the final result, and then we'll give it some interpretation. Is anybody opposed to me doing that? Yes?
I have a few questions.
Say it again?
I have a few questions.
Yeah.
The first thing is, okay, you first redefine a new derivative.
Yes.
Definition. Okay. So this is for the local
Transformation.
transformation.
Yeah, the one where the phi actually depends on position.
Okay. So, and what happened with the global? So you should change too? Or?
Well, actually, that's interesting. If you're invariant under a local transformation, are you automatically invariant under a global one? The answer is yes. Because one functional form of phi of x mu is that it's a constant. That's a function, it's just a constant. But if you're invariant under any form of phi, you're invariant under the constant form, which is a global transformation. So if you're locally invariant, you're automatically globally invariant. If you're globally invariant, you're not automatically locally invariant.
So in the global case, we will use also that new definition of.
Yes, yes.
Okay. And the other thing is that you say that the local symmetry at the end generates an interaction term. So
Yes.
local symmetry generates interaction term. Always.
Yes, yes. Okay, and I'm gonna comment on that in just a moment. Okay. But let me just scribble up our final result and give you some words of interpretation and identification. And then we'll look at some extensions. We'll start the extension story, but it's really gonna finish next time. But just let me say a few things. Oh. multi-Lagrangian ends up being this plus IQ H bar C psi bar gamma mu A mu psi plus MC squared psi bar psi plus 1 over 16 pi F mu nu Okay, where remember we're leaving off this term because if it's not massless, this thing is not invariant. Okay? Where of course F mu nu is d mu A nu minus d mu A mu. Recall, the entire story is invariant under the local transformation e to the iq phi of x. And then A has its own transformation rule, okay? But this is the sort of defining transformation of this story. Now, can anybody tell me what kind of transformation this is? Remember, transformations that are used in this class all form groups. Groups have different labels. Okay? Remember, groups you can form as matrices? What kind of matrix would this be? How many dimensions?
Is this U1?
Yeah, so this is what we call U1. That is, if I take an element of it and then I multiply it by the Hermitian conjugate, I get the identity. But these are just numbers, so this is really just complex conjugation. These aren't matrices. Okay? Now here's an important question. What theory did we just build? Anyone?
Is this electromagnetism?
This is electromagnetism. Remember when you were learning electromagnetism from someone and they mentioned gauge invariance? You remember that? Did they mention that that is the basic pillar upon which electromagnetism as a theory is built? No.
Was that someone like rabbits?
Okay, it turns out that electromagnetism in its full form is born from this argument that I want to take this global transformation and make it local. Okay? And by the way, these things right here, if you found the equations of motion from them, they'll be Maxwell's equations. Or half of Maxwell's equations. Remember, only 2 of Maxwell's equations are equations of motion. The other 2 are these electromagnetic geometry equations. But I'm sure you learned about that in your electromagnetism course as well. Sorry, I just feel like students learn so little about electromagnetism. You learn how to calculate, do dielectrics and all this shit. You never learn anything fundamental about it. Well, there you go. There's the most fundamental creation of electromagnetism. Now, you might say, oh, that's electromagnetism. That's cool. What about the others? Every force in nature can be built this way. The problem for the strong interactions and the weak interactions, as you might or might not recall, they are born under these kinds of transformations, strong interactions and weak interactions. These groups are non-abelian. If I take 2 of these and I do the commutator, I don't get 0. If I take 2 of these and do the commutator, I don't get 0. This is abelian. I can take 2 elements of this, commute them, I get 0. Okay? It turns out that the non-abelian nature of this makes this story more complicated, but we still follow the same damn steps, including getting a beer. Always get a beer. Okay? Next time, we will dive into this. This is going to include new degrees of complexity, but out of that is going to be born a very, very important observation about those forces. Okay? A very important observation, which is very distinct from electromagnetism. Oh, I have a question. Maybe I'll ask Cameron. There you are. You're hiding right now. it's a number. Yep, that's pretty good. Q appears here in this coupling term. Notice Q doesn't appear anywhere else. So in this coupling term, coupling the photon vector field and the matter that it's interacting with, I get a Q. What do you think that Q is, physically?
Momentum?
No? It's a scalar. That's the charge. Q represents the charge of the psi field. We know that charge plays a huge role. In fact, if I have a chargeless particle, Q is 0 and there's no interaction. Makes sense, right? Okay? All right. So, well, there's another way to think about this story, which is actually a bit cleaner. And it will help in looking at the non-Abelian case, but also relating this to another story. Let's look at the problem that we encountered in the following sense. So I had this, and I did my transformation, and I ended up with this. And again, phi is going to depend on position. I'm just not going to write that everywhere. Okay. So once again, the reason why in the naive story, without all of these nice terms, the reason why this didn't work is because this local term, because phi depends on space, cannot be moved past the derivative. Okay? We fix this, of course, by employing this new derivative. All right? Which in the end does this. So if I write this, then this becomes psi bar e to the minus iq phi gamma mu d mu prime e to the iq phi psi, where I'm writing d mu prime because the derivative itself has to be transformed, because the derivative, remember, involves a, and a gets transformed. Okay? It turns out that if I transform the derivative and I move this across it, I get exactly this. Oh wait, I can combine those to get that. Okay? So what we find is that d mu psi, the derivative of psi, transforms to d prime e to the iq phi of psi. And this is exactly what I get is the reversal of these and the transformation of this, which is iq phi d mu psi. This is the magical property of this new derivative. It's basically letting me take this transformation, commute it with the derivative as long as the derivative transforms in the right way, which we found how this should transform. So this always lets me move the transformation past the derivative. Okay? We like to call this a covariant derivative. Okay? That is, the derivative transforms in the same way that the psi field transforms. So what I'm saying is that, psi goes to psi prime, which is e to the iq phi psi. D mu psi goes to d mu prime psi prime, which is d mu psi. Oh, sorry. E to the iq phi d mu psi. So this is the really nice property of this derivative. It lets you move the transformation of the field you're taking the derivative of outside, which always means you can cancel it. Okay? Now I wrote it this way because imagine if the transformation I was doing was not an internal transformation where I'm just multiplying by some weird internal factor, but rather I'm taking the coordinates and I'm redefining the coordinates. I'm doing a coordinate redefinition. That's what that is. We can ask, if I do a coordinate redefinition, do I get the invariance? And notice this is a local coordinate redefinition because the new coordinates depend on where I am. Okay, so for example, going from linear coordinates to spherical polar coordinates is definitely a local transformation. If I just take a linear and I move it to another linear here, that's a global transformation. But going from linear or rectangular to spherical polar is definitely a local, okay? Well, it turns out that in a theory which has partial derivatives, this requires me, if I want it to be invariant under this, which physically it should be. I mean, it's a coordinate transformation. That shouldn't change the physics. I have to replace the derivative with some new derivative, which is the old derivative plus some very funny things called Christoffel symbols. They're gauge fields. Okay? These things are really weird objects because this is a transformation of space-time. Again, notice x mu itself doesn't transform here. It's just this phi, which doesn't have an index. But here, this has an index. So these things actually carry 3 indices. I'm not even going to write them up there because we can't. Okay? But this is just the important observation. I'm once again looking at a local symmetry, and I'm finding that by redefining the derivative in an appropriate way, I can have the theory be symmetric under this. Okay? Does anybody know what this might give me? I mean, I'm saying things give me interactions, right? Demanding local symmetries. Anybody have any idea what this might give me?
Interactions like self-interaction?
Well, I mean, this gives me general relativity. That fourth interaction, gravity, you remember? Okay. Once again, all I'm doing is I'm taking a global symmetry transformation, I'm localizing it, I'm doing so by redefining the derivative, and this once again generates an interaction, it's gravity. So I just want to stress to you, this whole idea of taking global symmetries and forcing them to be local underlies all 4 of our fundamental forces. Electromagnetism, the weak interactions, the strong interactions, and gravitation. The gravitational story is built out of slightly more complex things, so I won't go any further with it. Okay? These gammas, for example, they've got weird index structure, but it's the same overall story. I'm just demanding a global transformation be local. All right? So I'm going to quickly finish up, and I have plenty of time for this, to get to a different, or get in a different way to what the gauge invariant field strength is. So basically, I want to arrive at what this F mu nu should be. Okay? Because as it turns out, in the non-Abelian case, it will take a different form than this simple thing right here. All right? So let me just very quickly run through this. I'm probably going to regret having erased what I just erased, but that's fine. Okay. So it turns out that to find what I need for the kinetic term of the gauge field, one way to do it, which is sort of globally universal, is to just take the commutator of 2 of the new derivatives. okay? And then let them act on whatever the field is in question. So remember, in this story, we have that the capital D is lowercase d plus iq a mu, d nu plus iq a nu, acting on psi, minus d nu plus iq a nu, d mu plus iq a mu, acting on psi. Remember, I'm just doing the commutator of these, so this is d mu minus d mu. So d nu minus d mu, and it's all acting on psi. Okay? So let's see. I'll be detailed here. So I'm just putting these sides, whoops, inside of these parentheses. All right, now we can act on this term with this guy, and this is going to generate d nu psi plus iq a mu d nu psi minus q squared a mu psi plus iq d nu a nu psi plus iq a nu d nu psi. That's what I get from these terms, and then I'm just going to get I'm going to write down what I get from those terms. I'm going to get minus d nu psi minus iq a mu d nu psi plus q squared a mu psi minus iq d nu a mu psi minus iq, whoops, a mu d nu psi. Okay? Who's it going to be? Hannah. Hey, Hannah. I got 10 terms on there. Can you tell me which ones cancel?
The first one, but yeah, that was mine.
Do those cancel?
No,
Yeah, okay, what about these?
no.
Why not? Well, a mu, a mu. Can I just reverse the order of the a's? Yeah. So I can turn this into a mu, in which case these will cancel. These, yeah, I don't know about. No, hold on. D mu, a nu, d mu, a, yeah, no. Huh. Oh, wait a minute. This is this with a minus. Those cancel. And this is this with a minus. Those cancel. All I'm left with is iq d mu a nu minus d nu a mu psi. Well, this tells me that all I have to figure out for the form of f mu nu is that it's minus I over q times the commutator of d mu d nu. Okay? So again, when we played this story out, we took this f mu nu Lagrangian and added it in because we had to introduce this gauge field. And we used this definition of d mu a nu, or sorry, of f mu nu in terms of d mu a nu. Using this definition to get f mu nu gives me exactly the same expression. Okay? However, one of these will be useful for the non-Abelian case and the other one won't. This will be useless. This will be useful. So for our f mu nu's that we have to add to get the local gauge invariance, we're going to use this to define f mu nu. And our expressions for f mu nu in the non-Abelian case will be more complicated than this. But they will include some very, very illuminating stuff. Okay? But just so that the connection is obvious, if I do this for, say, a vector lambda using the capital D's from general relativity, then what I get is the relativistic equivalent of F mu nu, which actually turns out to be a rank 4 tensor. It's got 4 indices, one of the ugliest. This is called the Riemann curvature tensor. Just an advertisement for general relativity next spring if you're here to take it. But anyway, we'll go through that in detail. All right, that's it. Questions? Yes.
So when we went through the whole thing, built the Lagrangian that's at the top of the board, is that for a specific spin particle, or is that?
It's for a, so you're talking about this Lagrangian?
Yeah.
It's for any particle with charge, with non-zero charge.
Okay.
I mean, it's for an electron, it's for a positron, it's for a quark,
Okay.
okay? It's not for a neutrino. All right?
I have two questions.
Yeah.
The first one is, what I understand is that you follow that step, and then you use a transformation that is in this group U1,
Mm-hmm.
and then you say, okay, but if we work with this another transformation of this other group, we will find this other interaction.
Yes.
Right?
Yes.
So, what happens if I try with another kind of group transformation? Can I find another type of
Yes, yes,
interaction?
yes. You can pick different groups and you'll find different interacting theories. Actually, there's going to be a new ingredient to the non-Abelian story, which will be obvious next time, okay? But beyond that, playing with different groups is, I mean, you're gonna get different results for the actual group transformation, but it's not really gonna bring anything more interesting in if you play around with different groups.
Nothing like, I don't know, I was thinking, for example, in dark matter, the people who work in dark matter, it's like, okay, I will try with this and maybe I can find interaction with dark matter or something. I don't know.
Yeah. Well, I mean, for the dark matter, so first and foremost, we've got to get through the Higgs mechanism before we can even start to begin to talk about the dark matter story, because that's where the mass terms are going to come from, but we'll talk about that more in time. So maybe we should hold off on talking about dark matter until after we've covered the
And
Higgs mechanism.
My other question is that, okay, you started with the Lagrangian of the 1/2 particles,
Yes.
with that Lagrangian, and then you say, okay, and if we do the mass 0, we will find the case of electromagnetism.
That's the
on
mass
bottom.
0 here. That's
Oh.
not, this mass can be non-zero.
Okay.
These masses were fine. These terms were automatically invariant under the local gauge transformation. This mass term was not invariant because A transforms in a different way. It's A goes to A minus D IQ d mu. So this term is not invariant. This term was invariant. So you can have masses for the matter, you just can't have mass for the new particles that you're putting in, the A mu's.
Yeah, because it's like you're starting with the case of the fermions, and then I was thinking that you were jumping to the case of boson because the photon is a boson. So.
Well, I'm only jumping to the case of these vector particles because I've got to redefine the derivative. And whatever I add to it has to also have that vector index. That's plain and simple. I mean, I cannot add a spinor to it because this is a spinor plus a vector. That doesn't work.
Okay.
So it turns out that the field that I have to add, basically because you want it to take the same profile as the derivative, this field has to be a vector, a dual vector actually. But so this is the thing. You start this story with nothing but matter. No interactions, no vector particles, no scalar particles, just matter, spin-a-half particles. Identify a global symmetry and say, I want you to be local. And in doing so, you are forced to introduce a vector particle which interacts with the original spinor, okay? Right there. All right? But then you want to let that vector particle propagate, so you add in its kinetic term. And now you've got the full story of electromagnetism.
Okay, I see. Okay, thank you.
The phi in the transformation, does that have any relation to the phi in the spin zero Lagrangian?
No, yeah, no.
Okay.
This is a transformation function. This is not a degree of freedom. I mean, so this is not a degree of freedom in the Lagrangian. This is just a transformation parameter that you're using. The degrees of freedom in the Lagrangian are either scalars, spinors, or vectors. Unfortunately, we run out of letters really quickly, so that's why phi is used twice. But it's a good observation. Other questions? Yes?
Physically, is phi supposed to represent like a voltage or something? So what, like, physically is this gauge invariance then?
Well, I mean, it is the fundamental defining.
Right, but like,
No, so in your study of electromagnetism, what you learned was that the scalar potential and the vector potential, phi and ai, remember? Did you call it ai or a vector? That's the vector potential. Okay. Well, first of all, these just get combined into a new. Okay. And so in learning electromagnetism, one thing that you learned is that you can write electromagnetism in terms of electric and magnetic fields, or you can write it in terms of these. Okay? However, if you write it in terms of these, you're not fixed to a particular form of them, because there's these transformations you can do which change these but leave E and B fixed. That's where you learned about gauge invariance. Remember? You kind of remember that story? So when you treat these as your unknowns, you can freely make transformations on them to simplify solving for them. Those transformations are free because they don't touch the physically realized electric and magnetic fields. Okay? That's exactly local gauge invariance, because in the field theory approach, you don't even mention electric and magnetic fields. You work with this, and this is invariant under transformations, which we just realized. So it's funny, when gauge invariance is shown to you in electromagnetism, it's usually just this accidental symmetry, which is handy because it can help you solve equations. It's never sold to you as, this is the fundamental building block of this theory. But that's because very few people understand this, except for you guys.
The argument for this specific transformation that we got in quantum 2 was maybe not really physically correct, but made a lot of sense to me. It was that this is a phase transformation on your spinner. And so the global transformation is you're saying, I'm going to take the whole field everywhere, and I'm going to transform its phase.
Sure.
The argument for why you can promote that to the local is that then you can say, well, I'm going to do it, and I have no way to verify it because of this annoying thing that has the speed of light.
Yes.
So
Yeah, no, I mean, that's actually,
it has to be local.
yeah,
And then you get-
yeah. No, that's exactly right. It's impossible to take the entire universe and everything in it and do the same thing everywhere. Okay? So there's this relativity, and the speed limit of signal propagation being c kind of suggests this. Yeah. But honestly, like, here's the important thing. This is a way to build an interacting theory. It's a way. It's a pretty way. You could also just throw shit in there, anything you want. The question is does the result of this in calculations related to experiment give you the right answers? And the answer is yes. So this is correct. It's not the only interacting theory you could write down. I mean, I could write down an interacting theory that has an interaction like this. Okay? Yes, I've introduced a new field, the smiley face field. You can create that theory and do calculations with it. It's just not going to match what we measure in an experiment. Now, I say all that, But I should give you one final comment. Let's get out of here. One final comment. And that is, this is not the end of the story. It turns out that to really get a good and accurate description, we actually have to add into the theory every single term like this. Every one of them. But that will be a detail we explore at the very end of the semester. That's a doorway to string theory. But more on that later. All right, thanks you guys.